Welcome back, everybody. So this is that extra practice problem. This is the reason why the answer is 1/3. If you'd like to take a picture of it, you're more than welcome to, because that's for educational purposes. That's chill. The key thing is finding a common denominator. And since the second term, the 3 over k squared plus 3k, it has a common factor of k in it. So you only need to multiply the first term by something that's missing for the LCD. And then that ends up canceling the 3's, which allows you to cancel the k's, which allows you to plug in 0, and you get 1/3. And then I had asked you guys to do these two problems over the weekend. Here are the answers. Not those ones. These two. Here's the answer to part A, if you'd like to take a picture of it or whatever. In short, you plug in 6 and you see that you get 0 over 0. So you have to factor it. But we know that since t is at 6, it equals 0. That means that t minus 6 is a factor of both the numerator and the denominator. I didn't need to use that for the denominator because I saw that if I factored out a t, it was a difference of squares. That's why I've got t times t plus 6 times t minus 6. And one of the factors of t minus 6 gets canceled. And the t minus 6 in the denominator, that was the thing that was causing issues because we don't want to be dividing by 0. So I cancel it out, and then I can plug in the value. I get 6 minus 6 up top, which is 0, and 0 divided by anything that's any non-zero number is 0. So the answer is 0. Any questions on that? The next one, and you can also take a picture of this one if you'd like, is a conjugation. So you try and plug in 0, or you try to plug in 5 for x, and you get that it's 0 over 0. So you have to do some type of algebra to fix it. And in this case, it's going to be that you multiply it by the square root of 3x plus 1 plus 4 over square root of 3x plus 1 plus 4. And that means you're multiplying conjugates, which becomes a difference of squares. So you get square root 3x plus 1 squared, which cancels the square root, minus 4 squared, which is 16. And then, so when you simplify the numerator, you get 3x minus 15, which there's a common factor of 3 that can be factored out. The x minus 5's cancel. And then you've got 3 over the square root of 3x plus 1 plus 4. We got rid of the problem, which was the x minus 5, and we get to plug it in, and we get 3/8. Any questions on either of those? Yes.
First one?
Yes.
You're right.
Cool. All right. Any questions? Any other questions, rather? Okay. So, the squeeze theorem. Once again, if two functions are sandwiched, if one function is sandwiched between the other two, and the outer two functions have the same limit, then by necessity, so does the middle function. That's kind of what the squeeze theorem does. So, for example, use the squeeze theorem to determine the limit as x approaches 0 of x times sine of 1 over x. Now, one might want to be able to just break it up into two pieces and find it that way, but unfortunately, it doesn't work because the limit as x approaches 0 of sine of 1 over x does not exist. We saw that in the first unit 1.1. Sine of 1 over x, its limit does not exist. And so we can't break it up into a product because if you go backwards, don't worry, I'm coming right back to it. But the theorem for algebra for limits says, suppose that the limit of f and the limit of g both exist. You can only use these rules if both limits exist. So we can't just look at it separately and figure it out. We have to figure out something else. Where were we? Right there. Okay. So the goal when you're dealing with the squeeze theorem is to find bounds, find an upper bound and a lower bound. And so one thing that's a very, very useful fact is that sine of anything, what is sine always bounded between? -1, yeah, -1 and 1, -1 and 1. and -1 is less than or equal to cosine of blah is less than or equal to 1. Sine and cosine have a very nifty property, which is that they are always bounded between 1 and -1. So in particular, we now have, therefore, -1 is less than or equal to sine of 1 over x is less than or equal to 1. Now, I know that doesn't seem like that big of a deal, but it actually is. Because the middle thing inside this compound inequality, it's very, very close to what we need. So what we can do is we can multiply this entire equation by x. And so we've got -x is less than or equal to x times sine of 1 over x is less than or equal to x. Now, you should be questioning me on that math. Phil, you just multiplied an inequality by a variable. That's a no-no. When we did that type of a thing, we got batted on the nose as a bad student. You don't do that. And they rub your nose in it because the problem with variables is that variables can be positive and they can be negative. So if I multiply by x, that might change the direction of the inequalities depending on what x is. However, because it's -1 and 1, it's all okay. It's all gravy. If x ended up being negative, then the left-hand side would be positive x and the right-hand side would be negative x, and the inequality would flip, but it would be all chill. So technically speaking, this is a bold thing to do, to multiply an inequality by a variable, but because of the fact that it's bounded between -1 and 1, it ends up being okay. So anyways, now that it's bounded between these things, now we have a bound, an upper bound and a lower bound for our desired limit. And as x goes to 0, -x will go to 0, right? Because it'll be -0, which is 0. And x will also go to 0. So, by the squeeze theorem, by squeeze, this ends up being 0 as well. The limit as x approaches 0 of x times sine of 1 over x actually ends up being 0. So even though sine of 1 over x did not actually have a limit, right? We found out both by numerically guessing and by looking at it graphically that the limit did not exist. But tacking on that extra multiplication by x is just enough to make it actually exist, which is pretty nifty. There's another proof of why this is true that doesn't require the squeeze theorem, at least not technically. But that'll be something for later. In fact, right now. Some special limits. Now, I do not like this limit, and there's a reason for it. So I love it, but I also hate it. So the limit as theta approaches 0 of sine of theta over theta, that equals 1. As a special limit. And then by consequence, if you have theta over sine theta, that also equals 1. And then there is another one, which is 1 minus cosine theta over theta. It equals 0 as theta approaches 0. The reason why I dislike this one is when I first started out making these notes, I had a beautiful proof that I had made with all these cool, pretty graphs. And I originally started writing my program, my graphic, my lecture notes. I was using Word to do it. And Word and Apple products did not agree back in the day. And so if you added too many graphics, it would wipe out the entire data. And so I moved one thing after saving it, and then I resaved it as a PDF, and everything was gone. So threw it out and said, no, now nobody gets to see the proof. Now nobody gets to see it. So there is a proof of it, of why sine of theta over theta goes to 1 as theta goes to 0, but you're not going to see it. I'm too hurt by it. It's like the Super Bowl for the Seahawks, that last one, which, once again, we're all super stoked about it. Going to Super Bowl again. It's excellent. It's a good day. It's a good day to be a Hawks fan. Anyways, so You do not need to have these memorized. Yeah, you don't have to have them memorized. I'll provide them. I'll provide them if they're needed. But you need to know how to work with them. So, this first one, the limit as x approaches 0 of sine of 3x divided by x. There's a problem there. The problem is that it's, so how did I want to write this? How did I want to say it? How did I want to say it exactly? So this one's a delicate procedure. So this looks like the special limit, but it's not. So we're going to put a little comment and say the special limit says sine of theta divided by theta. It's the same variable in both places. This is not sine of x over x. This is sine of 3x. So that's an issue. But it's not that big of an issue. And I'll explain why. What we can do, and I wouldn't expect you to know this, is to multiply. So I'm going to cover that up and multiply it by 3 over 3. Just for a second. Then this will be the limit as x approaches 0 of 3 times sine of 3x divided by 3x. Yes. Now there's a myriad of ways we can prove this, but what I'm going to tell you is that 3x, sine of 3x over 3x, that goes to 1. So this equals 3 times 1, which is 3. You don't need to write the 3 times 1. I was just mentioning that so that we know that the 3 was a constant, so we ignored it. And then the sine of 3x over 3x equals 1 when you take its limit as x approaches 0. Now, there are many different ways we can verify that. There are two main options. And we'll just focus on one. The reason for this, I'm going to put an asterisk. The reason is we're going to let y equal 3x. Then, as x goes to 0, what does y go to? 0 as well, right? If x goes to 0, 3 times 0 is 0. So as x goes to 0, y goes to 0. Thus, the limit as x approaches 0 of sine of 3x divided by 3x, that's equal to the limit as y approaches 0 of sine of y over y. And that's the special limit. And that equals 1. That's one way to talk about it, is to say, if I make what we call this a substitution. So we're changing the variable, and when we change that, we change luckily for us, the limit value 0 didn't change. But if this was 3x plus 1, the limit would go to 1. Let me say that out loud instead of let me write that down for just a second. If y was equal to 3x plus 1, then as x goes to 0, y would go to 1. So this would change to a 1 and stuff, but that's not the case. It just so happens that it works out for us. So, do you have a question? What's up?
If it wasn't sine or cosine, what happens if it's tangent?
What happens if it's tangent? That's an excellent question. It's an excellent question. What happens if it's tangent? Well, we can utilize trig identity.
Sine and do the same thing.
Exactly. So Alex was saying what we can do is if we have a tangent involved, tangent can be converted into a sine over a cosine, and then you can work with it. This next, we're going to do B, and then we're going to skip C and go to the next page for just a moment after that. So this one, 1 minus cosine t over t squared minus 2t. The temptation would be to just try and plug in, just try and work with it. We should try and plug in 0, but if you do, you will get 0 over 0. That's a big no-no. But what we can do is realize that this is t times t minus 2 in the denominator. And then, by properties of fractions, we can split this up into two fractional pieces. We can rewrite this as the limit as t approaches 0 of 1 minus cosine of t over t times 1 over t minus 2. And that's a special limit, 1 minus cosine t over t, that goes to 0. And then 1 over t minus 2, that goes to negative 1/2. So we get 0 times negative 1/2, which is 0. Oh, and I've been meaning to show this. I've been meaning to talk about it, but I forgot. When it comes to checking your work. So, people watching the recording, sadly, you won't be able to see this. So I'm just going to even pause it so we don't, so you're not just waiting around. So I'm going to pause it real quick. Okay, so during that little pause, we were showing how to use your calculator to check your work with the numerical guessing method. So if you're watching the recording, just come talk to me and I can show you how to do it. Unless you can do it on yourself, by yourself. Okay, so before we go, Eli. Hey, yes. Before we go on to the next one, we're going to learn a theorem to handle this situation much easier. There is a method that will make this problem far more approachable. Is it okay if I move, or no, you're still right?
Yeah.
All right. So there is a generalization of that special limit. And it says, suppose that the limit as x approaches c of f of x is equal to 0. And it's never 0 around c. That's kind of a little extra stipulation, but we never really have to worry about that in this class. That's mainly for math majors to deal with in formula math courses. Then the limit as x approaches c of sine of f of x over f of x is equal to 1. So the same thing is happening. The inside is going to 0, just like it would here. The inside is going to 0, because if theta is going to 0, the insides are going to 0. Here, f of x is going to 0, so the insides are going to 0. That's a nifty little trick. So if you can ever get it to be sine of something divided by that exact same something, you're golden. So for example, before we go back to the previous page, we've got the limit as x approaches 1 of sine of ln of x over ln of x. If you try and plug in 1, you will get sine of 0 over 0, which is 0 over 0, so it's no good. But we notice that the inside function is the same function. They're both natural logs. And we might note something. Note the limit as x approaches 1 of ln of x is equal to the natural log of 1, which is 0. Good. We all remember our logarithms, right? Log base b of 1 is always 0. So this fits into the definition, meaning that the answer is just 1. By the theorem above. THM abbreviates to theorem. It's one of the big things that you might notice in mathematics that's different than a lot of other sciences. It's we don't write theories. I mean, there is theory, there's a study of something, like there's ergodic theory, there is chaos theory, but in terms of any like things that we study, they're always theorems and stuff. Because we're cooler than the rest of the sciences. we know things to be absolutely true, and there is without a doubt that it is proof. And that there is without a doubt that the thing is proven. Like, yes, the theory of gravity is all but true, but like if one person was able to find one specific spec where it didn't work, then we would have to have a conversation about it. But theorem is a cool word. Anyways, I'm getting sidetracked. Okay, so back to yes.
It's just to be signed, it's just have to be signed for this theorem to work.
Yes, it has to be signed. So let's go ahead and do this one before we go onwards, but go backwards actually. Sine of 2t minus 3 over 2t squared plus 5t minus 12. You might want to try and plug in 3/2 and hope that you get something that sticks, but it won't. It'll give you 0 over 0. If you try and plug it in your calculator, you'll get a math error. So, but seeing as 3/2 gives us 0, that means that t minus 2/3, which could be written as 2t minus 3, is a factor. This thing factors to the limit as t approaches 3/2 of sine of 2t minus 3 over 2t minus 3 times t plus 4. And 2t minus 3 goes to 0 as t goes to 3/2. So it fits into the theorem. That fits into the theorem that we want. In particular, this piece right here. Yeah, I totally wanted to do an oval. There we go. This piece goes to 1. It just does. By necessity. By the theorem. So the answer will therefore be... Oh, well, before we continue. That gets rid of the problem. The problem was the 2t minus 3, because that's what was giving us 0 in the denominator. Now that we know that that's gone, we can plug in the number and have a grand old time. So it becomes 1 times 1 over 3/2 plus 4. And 3/2 plus 4, 4 is 8/2, 11/2, so 2/11. And that's our answer. Yes, JT.
I just like the last portion of it.
After the green or so right here?
Yeah.
Sure. So let me erase this actually and make sure that it's green. That's the green one that we got. And then here, 3/2 plus 4 is equal to 3/2 plus 8/2, which is 11/2. And so we're doing 1 divided by that. So you flip and multiply, that's where we get the 2/11. So 1 divided by 3/2 plus 4 is equal to 1 over 11/2, which is 2/11.
Yeah.
Excellent. Okay. Any other questions? All right, so back to this one. I love this question. Does anybody need still time? I think so. A couple people still writing. Let's look at the calendar. Let's make sure. Am I on track or am I off the track? Okay, cool. So we're going to be continuing 1.3 on Thursday. So that's good. I learned my lesson, I think. Last semester, I tried to shove it in one day, and that wasn't enough. All right, good. So back to this one. Sine of 2y over sine of 5y. So this one, I put it on an exam before, and students just really write the answers 2/5. I need to know why. I need to know why. And so what I'll do, does anybody have an idea? Like terms? There is an idea of trying to get like terms with a 2y and stuff, but there's no y's. There's no y's on this. So
Can we multiply by 2y over 2y and 5y over 5y?
that would be an option. So there's many different ways we can do it, But Eli is exactly right. We'll multiply by, well, actually, not by 2y over 2y. What we're first going to do is we're going to multiply by 1 over y over 1 over y, which is cleverly multiplying by 1. There are many different ways to do this, by the way. If you look up one of these problems online, they might solve it a different way. But we're all in agreement. I can multiply by 1 over y divided by 1 over y, because that's just multiplying by 1. So this becomes the limit as y approaches 0 of sine of 2y divided by y all over sine of 5y over y. And this gets to Eli's idea of trying to get an over y situation. And then we're going to take JT's idea of trying to find like terms. We want it to get to be where we want it. We want a 2y in the denominator of the big numerator. We want a 5y in the denominator of the big denominator. So we're going to do again, we're going to cleverly multiply by 1. This time we're going to multiply 2 over 2 and by 5 over 5. Which gives us the limit as y approaches 0 of 2 times sine of 2y over 2y divided by 5 times sine of 5y divided by 5. Ta-da! So, y. So once again, we're trying to get that 2y down. People watching the recording. We're trying to get a 2y here. So we have to multiply by 2, but we can't just multiply the denominator by 2. That's not allowed. So we have to cleverly multiply by 1. That's why we multiply by 2 over 2. And the same argument goes for the big denominator, the sine 5y over y. And then I suppose I could just bring this up here if I wanted to, and bring this up here. Actually, I'm just going to go like that. And then it's maybe a little more approachable. And the whole point is that as y goes to 0, 2y goes to 0. So that's our f here. That's our f function in this definition, or this theorem. That's our f of x. So that means that this goes to 1. And this also goes to 1. So we've got 2 times 1 over 5 times 1, which is 2/5. You can skip that 2 times 1 over 5 times 1, but I just wanted to mention. Actually, I'm going to even color code it. Yes, Joe, right?
Yeah, what happened to the bottom y in the denominator?
What did happen to it?
You didn't write like what?
I didn't write it. I forgot to.
Okay.
Thank you. Thank you for catching that. I was testing you guys, see? Good. Good that we caught it. Caught it. All right. That's a tricky one, but it's kind of fun to do that, just to mess around with these things, multiply. Like, this is all about algebra. This is all cleverly multiplying by 1. We did it 3 times here. All right. Let's take our break. Let's come back at 103. 103. People watching the recording, go do some guided meditation. Okay, so we go on to one-sided limits. One-sided limits. So this is unit 1.4. There we are. There you are. So for the motivation for this concept, mathematicians, we wanted to have something to define specifically at maybe endpoints of a function. Because what would be the limit of, here's a good idea. Don't need to draw this. The square root function, right? Remember what it looks like? Looks like that. And it's only defined for numbers greater than or equal to 0, right? What is the limit at 0? We should be able to say that the limit at x as x approaches 0 is 0. That would make sense. But how do we do that when we can't approach it from the left? And there's a little bit of haywire, like hand waviness about this situation where you can actually say that the limit as x approaches 0 of square root x function is 0. But this kind of brought up the idea of maybe just looking at one side of a function to find its limit. So in particular, we looked at that one example of absolute value of x over x. And we established that the limit as x approaches 0 does not exist because on one side it approached 1, and on the other side it approached -1. So that gives us the concept of a right-hand and a left-handed limit. The right-hand limit of f of x as x approaches a equals L if we can make the function values get arbitrarily close to L by taking x to be sufficiently close to a with the stipulation that x must be greater than, i.e. to the right of a on the number line. Intuitively, it's the tendency of the y values of the function values, as the x values get closer and closer from the right. That's the main thing we need to take away. The other version is for more mathy things, like use those epsilon delta definitions. So the way we write it is the limit as x approaches a, but we use a plus symbol for its exponent of f of x equals L.
That means on the right.
Mm-hmm. So to think about that, the reason why it's a plus for the right and a minus, the left-hand limit going to be very, very similar, but instead of a plus, it's going to be a minus. So the left-handed limit is the limit as x approaches a with a minus sign, meaning from the left of f of x equals L. Now, the reason for that is to think about a number line. If here is a plus is over here. It's a little bit more than a. So it's a little more positive. It's a little further right on the number line. It's a little more positive. That's why it's a plus. Whereas a negative is over here. It's a little bit less. It's a little bit smaller. It's a little more negative. A little closer to the negative numbers. That's how we interpret it. This is probably the most useful thing you will ever use in your life, in your daily life. And I'm going to show you how. So I love cooking. And you know when a recipe calls for like a cup of flour and you're like, it needs a little more flour, right? It like 1 cup of flour doesn't work. Or maybe you like it to be a little spicier or something and it says 1 teaspoon of cayenne pepper and you want a little more than that. Instead, you write on your notes, you write 1 plus teaspoon. To write like, and then you get to have calculus in your cooking. You know, just a little bit more. And that way you don't have to say like 1.1 teaspoons or whatever. You just say 1 plus, and then you look like a badass and like way cooler than everyone else with your cooking recipes. And then like they ask you what's going on. It's like, well, that's just a calculus notation. You'll get there. And you can pat them on the back and explain it. Say what?
Yeah, that was one of the best you have ever.
This is the best use of it.
That's not one of the worst.
You know, like you disagree? It's the thing I use the most in my daily life, honestly. The 1 plus, the 1 minus, that's something I do use in my daily life. So, going back to this example, the limit as x approaches 0 from the right, 0 plus, is equal to 1, if you remember the graph of it. So just like, I'm going to put the graph here so we can see it. We had, here's 1, here is -1, and our function was an open circle here, open circle there, and it goes like that. So if we approach 0 from the right, our y values approach 1. But if we approach 0 from the left, our y values approach -1. Any questions on that? That's how we use left and right hand limits. I still remember one of the first times I had a student when I was a TA who was always a heckler with me. He didn't like the fact that I was too funny. He thought it was corny, which fair. fair thing. But he would mutter under my jokes and said, "No one cares. You're stupid." This is a really hurtful thing. But I got my revenge when he came in the last week before class and asked what the plus was and the minus was. I was like, "You clearly have not been paying attention. You're gonna fail the final if you don't remember what a to the plus, a plus means."
Would have been funny if you said you would get there.
Say what?
Would have been funny if you said you would get there.
You'll get there. just a little bit more, and you'll be right. Get it? Okay. Next theorem. Important fact about limits is that the limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the right of f of x equals L, and that also equals the limit as x approaches a from the left of f of x. If and only if statements are very, very powerful in mathematics. Whenever you see an if and only if statement, it's one of the most important statements. It means that it's true in either direction. So if you know that the limit exists, the full limit, just so we're clear, I'm going to call it a full limit versus a one-sided limit. So if a full limit exists, then the left and the right-hand limits both have to equal that number too. But the far more useful application of this thing is to check the left and the right-hand limits. If the left and the right-hand limits agree on a number, then the full limit equals that number as well. So we'll see that in this next problem. If the left and the right-hand limits agree, then the full limit exists and also equals that number. So the limit as x approaches 2 from the right of h of x. So we'll color code this. 2 from the right is 3. That's right. But the limit as x approaches 2 from the left is 1.7-ish. Wasn't perfect. I forgot to make this a little bit better of a function. So, oh well. Is roughly 1.7. So now we could look at this and say immediately, well, of course, the limit as x approaches 2 doesn't exist. But now we have a more formal reason why it doesn't exist. Because the left and the right-hand limits don't agree. So it does not exist because the limit as x approaches 2 from the left of h of x does not equal the limit as x approaches 2 from the right of h of x. Any questions on that? Now we have more formal ways to explain why a limit doesn't exist. I'd like you guys to figure out the second part, the limit as we approach -2. I'll slowly fill in details. You should get 4, 4, and therefore 4. That's a lot of 4s. The reason for it is as you approach 2 from the -2 from the right. So we're thinking about numbers like -1.9. That's a number that's slightly larger than -2. That's a weird thing to think about. I'll ask you a question in just a moment. But the negative numbers are a little bit weird when it comes to left and right. The slightly larger number of -2 is like -1.9 because it's further right on the number line. Whereas if we're approaching -2 from the left, we're thinking about numbers like -2.1. That's more negative. -2.1 is more negative. And so we no matter how we do it, we always approach the y value 4. Our tendencies of our y values go to 4. And since the left and the right hand limit give us the exact same number, the full limit must be that same number. JT.
Is that how the answers are supposed to be written, like on tests? Not like if it's asking the limit four is fine, or do we need to write like limit of x approaches to?
I see. Excellent question. So if it's a full limit and we know it exists, then you can just write the limit. So with this one, writing that the limit is equal to 4 is good enough. Writing that the limit does not exist unless I ask why. So if I say justify your answer, then you need to provide a mathematical reasoning. So that's a great question. So if I say explain why, then we need some mathematics behind it. That's when you'll bust out the one-sided limits or some other terminology that we learn later on. Okay? Yes. Yes. It's D and E because the left-hand limit and the right-hand limit do not agree. And they can, like, the function, like the full limit will only exist if the left and the right-hand limits are the same. Yes.
Sorry, just to confirm, so that's just confirming the theorem, we just went.
Exactly. This problem is mainly to show how to use the theorem. We'll be using it far better in a little, like we'll be using it in algebraic problems in just a moment. Instead of, because like with graphical ones, it's not nearly as useful to like prove something's true. So let's go ahead and we'll do 1.3.2 together. And then I'll have you guys do 1.3.3 on your own. So the limit as x approaches -1 from the right. -1 from the right would be from numbers like -1.7, -0.7, -0.8, -0.9, -0.99, -0.999. And we see that our y values approach -2. Whereas if we approach -1 from the left, we're thinking about numbers like -1.1 or -1.001 or -1.000001, and our y values start tending towards 1. So we can answer the question down at the bottom. Does the limit as x approaches -1 exist? No. The left and the right hand limits do not agree. So it's D and E. Now, granted, the answer to that problem, you would just write D and E on an exam or on a quiz. You just say it does not exist. Then we'll go on to the next one. The limit as x approaches 3 from the right. 3 from the right approaches 5. And 3 from the left, also 5. So the full limit does exist because they're both equal. And we didn't even really need, like, but once again, we didn't need to have the one-sided limits to figure that out. We could just see it and figure out that the answer would be 5. Last but not least, limit as x approaches 2 from the right would be 2. But from the left, it's 0. So the full limit does not exist. All right. Any questions on that one? Before we get started, like before I have you guys go off and work on the next one. All right. Cool. Go ahead and start working on it if you haven't already done so. Then we still need this up here to write. Okay. And you got my email with it, right? Yes. Oh. I see. All right. I'm going to move over to this one and go ahead and work on it if you haven't already done so. I promise next time it'll be a little bit better. It's hard to read on that one, like where the actual tick mark is, but it's at 2.
It should be -2.
-2, -2. Thank you. I wrote the line and I thought that was my negative. So -1, -1, -2, -2. And then 2 from the right. -2. 2 from the left. 1. I have the answers up here if you'd like to check your work. If you're still working on it, continue to do so. If you got them right, kudos. If you got them wrong, try and figure out what mistake was made. And if you can't figure out your mistake, feel free to ask. Yes, Jose.
Oh, never mind.
You got it? Excellent. All right, we all good? Do we have any questions on it? Or we okay moving on from this one? I get -1, -1, -2, -2, -2, +1. Lots of 2s and 1s. And thusly, since the left and the right hand limit as x approaches -2 were both equal to -1, the full limit is equal to -1. Same thing for the limit as x approaches 4. And then last one, the left and the right hand limits did not agree, so the full limit does not exist. But once again, that is just to showcase the theorem. On an exam or on a quiz, if I asked you to find the limit as x approaches 2 and I didn't say to explain it, you could just write DNE. You wouldn't need to justify. Okay. And that's great and all. That's great and all, but how do we do it algebraically? The good news is that because of their construction, because of how they're defined, they obey basically all the same laws that the regular full limits do. So the limit of a sum is the sum of the limits. The limit of a product can be broken up into a product of limits, and so on and so forth. But there's a little bit that we need to be careful about. Sadly, one-side limits have their quirks. Sometimes it will matter which side you approach from. Just like my mom, she's deaf in one ear. So if I approach on the left, she won't see me. It matters sometimes. It doesn't matter for everybody, right? Most of us have good hearing. We can handle it. But no, that's a lie. My mom is actually not deaf in both ears. It's just a fun little way to make it relatable. But that's the idea. Sometimes with these things, we need to be careful. Case in point. The limit as x approaches 0 from the right of square root x equals 0. Because if you think about trying to play and to verify it for yourself with like to kind of confirm it to yourself with guessing numerically, plug in 0.01, the square root of 0.01 is even smaller than that. Square root of 0.000001 is basically 0. So this thing will, the tendencies of the y values will tend towards 0. But big red baboon butt, the limit as x approaches 0 from the left of square root of x does not exist because we can't approach it. We saw the picture of the graph, right? The limit, like the function didn't exist before 0. We would try, and furthermore, if you want to think about it without a graph, try and plug in -0.01. The square root of -0.01 is not a real number. It's a complex number. And we are not interested in complex numbers. We should be. They're awesome. And if you want to know more about them, please feel free to talk to me. They're my favorite thing in mathematics. But look, for this course, we are strictly dealing with the real numbers. And the square root of -0.01 doesn't exist. So the one-sided limit from the left does not exist.
Doesn't it just turn imaginary?
Yes, so technically speaking, it will like if we were able to extend this function to the complex plane, yes, the answer would be 0. But that requires us to be able to see in 4 dimensions, and none of us can do that yet. Oh, there's a really cool program somebody did. I should send out a video. There's a thing that helps you visualize what the 4th dimension would look like, what it would be to be a 3-dimensional being living in the 4th dimension world, and it's really, really cool. He does it like I'll send out a video. It's awesome. Highly recommend. Sorry to get sidetracked, but 4 dimensions is cool. So main thing is main idea. Be careful with functions that have domain issues. Like square root, 1 over blah, and natural log of blah. Those types of things. Those are the ones where we need to be careful, right? Because they have domain restrictions. The square root, you need to make sure that the inside is greater than or equal to 0. Logarithms, you need to make sure that the inside is strictly positive. It can't be 0. 1 over something, you got to make sure that it doesn't equal 0. Those are the ones where we need to be a little bit careful on. Mostly, though, just the square root and natural log. Those are the big ones. So, for example, the limit as x approaches 3 from the right of e to the x minus 5 over natural log of x. This is trying to look scary when it's not that scary. The fact of the matter is, one thing we, just like with regular limits, we try to plug in the number. I see that I have a natural log. And that does worry me a little bit because natural log has places where it's undefined. But 3 is not one of those values, nor is a number less than 3, like slightly less than 3. So I don't have to worry about it here. So I can just try x equals 3. And boom, it works. You get e to the 3rd power minus 5 over natural log of 3. No issues. So that's the limit. E to the 3rd power minus 5 over natural log of 3. What is that number? I have no idea off the top of my head. E to the 3rd power would be roughly in the 20s. Divided by, so like maybe like 19-ish divided by natural log of 3. Natural log of 3 is like 1 point something. So probably like 18, 19. Doesn't matter. But you can check your work, plug that into your calculator, write it down, and then try and test. Say what?
13.7.
Darn, I was off. I was hoping I was. E cubed is probably not as big as I thought it would be. What is e cubed? 20. I thought it was going to be larger than 20, but it's 20. Okay, cool. Not that that matters. That is not a very useful thing to know. Anyways, good. So, any questions on that one? So if it doesn't have any problems around it, like 3, the one that I would be worrisome around would be 0. 0 would be something I'd be worried about. 1 would be something I'm worried about because natural log of 1 is 0. But other than that, I'm not too worried about this one. The square root, that's an, oh, JT.
So in plugging it in, stuff we don't need to worry about it's not a plus or because it's plus or minus, but it's not negative. We don't need to worry about that sign at all.
Because it was just asking for the right side limit. Then we've got the limit as t approaches 2 from the left of the square root of 4 minus t squared. So we try 2. Try t equals 2, and we get the square root of 4 minus 4, which is 0. But square roots can be finicky. How do you spell finicky? Is that how you spell finicky? spell finicky. I was right. Excellent. I thought it might have two N's. Finicky. No, that's finicky. Okay. But square roots can be finicky, so we should check it, because especially this is right at its dividing value. It's right at its dividing value. So let's check by trying t equals 1.99. Right, we want to try 1.99. That's a number slightly less than 2. And you could verify it another way and say, well, okay, if we're approaching, we'll give another explanation in just a moment. But if we do that, we get the square root of 4 minus 1.99 squared, which is approximately, let's do, well, it should be 0. So let's try 1.99999. Yeah, 1.999. You get approximately 0.019. And so that's with just being there. But remember, we're trying to approach it. So really, we should be using numbers like 1.99999999999 and seeing if that gives me an answer that's close to 0. And it will. So this one does, in fact, equal 0. But on a note, the limit as t approaches 2 from the right of the square root of 4 minus t squared does not exist. You could try it, and you'll see that if you try and plug in a number like 2.01, you'll get the square root of a negative number, which doesn't exist in the real numbers. It's complex. So there are certain cases where we have to be careful. Mainly just the square roots and the natural logarithms. As long as those are good, we're fine. Here's another alternative. Here's how you would answer it if this was if this was Calc Honors or Calc for math majors. This is how we would write it. So alternative explanation. As t approaches 2 to the negative from the left-hand side, 4 minus t squared, what will that approach? Will that approach, like, that'll definitely approach 0, but will it approach 0 from the right or from the left? From the right. And and if you don't see why, take a number like 1.9. 1.9 squared is slightly smaller than 4. So we're taking 4 and subtracting a number slightly smaller than 4. And so that'll appear, and then the closer and closer you get to 2, the smaller and smaller it gets, but it's still positive because we're taking a positive 4 and subtracting a number smaller than it. So it ends up being a result that's positive. As such, the square root of 4 minus t squared approaches the square root of 0 plus, which equals 0. On the flip side, if you're approaching 2 from the right, 4 minus t squared will approach 0 from the left, because you'll be taking 4 and subtracting a number slightly larger than 4, which will make it negative. And so that's why the limit does not exist for the right-hand limit. Any questions on that? Okay. Let's get into the more fun ones to work with. So the limit as x approaches 7 from the right of 3x minus 21 over x squared minus 6x minus 7. As per usual, we should try and plug in the number. Try x equals 7, and you will get, lo and behold, 0 over 0. As a reminder, this thing that I'm writing in green, this is something that we're writing for our notes, but you don't need to write it on an exam or a quiz. It's mainly something we're checking in our calculator or checking in our heads. So save yourself some time on the quiz or an exam. You don't need to write that. But anyways, that means that 7 is a factor of the numerator and the denominator. So this becomes the limit as x approaches 7 from the right of 3 times x minus 7 over x minus 7. And what do I need to multiply x by to get x squared? 1x. And what do I need to multiply negative 7 by? A plus 1. and the x minus 7s cancel. And that was the only thing that was causing issues with this limit. The only thing that was really causing a problem was the fact that when we plugged it in, we got 0. Now we've gotten rid of it, so we can evaluate the limit, and the answer becomes 3 over 7 plus 1, which is 3/8. Now, I deliberately made this one on one line so that I should have said that beforehand. I need to write something up here before we do this next one, because this next one involves an absolute value, which sadly Math 126 doesn't spend much time on at all, and neither does 127. So we don't really get to know too much about absolute values, which is a disservice, but I don't make the rules. I just have to follow them. Maybe one day I'll be a chancellor for this for the school board, and then I'll be able to change things. But that's a long time ago. That's a long time in the future once my son's out of school. So, okay. Now, I'm going to show something that's wrong for this one, because you could try and plug in 5 and you'll get 0 over 0. So this is incorrect though. The limit as x approaches 5 from the left of absolute value of x minus 5 over 2 times x minus 5. And John Doe student, silly John Doe, always getting into trouble. John Doe crosses these out. Why can't he not do that?
Cancel out an absolute value.
Exactly right. One of them is a factor of x minus 5, and one of them is an absolute value of x minus 5. They are not the same thing, so they cannot be canceled out. So what are we to do?
We're gonna do 1 time x minus 5, 1 time minus x plus 5, right?
So one time, sorry, what do you mean exactly?
So like we will give the absolute value for like x -5,
Mhm.
then negative x plus 5. Two situations.
So if it was a full limit, but this is a one-sided limit. So Eli is talking about a full limit with an absolute value. And that will be the way to do it for that one. But this is just the left-hand limit. So key fact about absolute values. ABS value. The absolute value of something is equal to one of two things. It's either equal to positive version of the thing if the thing is positive, but it's equal to negative the thing if the thing is negative. That's weird to look at, especially in these generic terms. I'll give an example in just a moment, and we'll practice this a couple times. But the fact of the matter is, what does an absolute value do? An absolute value, in short, if your number is positive, it fizzles out. Like getting a counter spell on a spell in Magic the Gathering, it fizzles. It doesn't happen. Not that I would know. I've never played Magic the Gathering before, but if I did, that's what happens. It fizzles. Whereas if the answer is negative, then it makes it positive. But how that mathematically happens is you tack on an extra negative sign on it. So for example, as an example of this, the absolute value of x plus 1 is equal to x plus 1 if x plus 1 is greater than or equal to 0. Sorry, I should put a greater than or equal to 0, not that, though it doesn't really matter where you put it. And it's equal to negative the quantity x plus 1 if x plus 1 is less than or equal less than 0, i.e. x greater than or equal to -1. If your x values are greater than or equal to -1, then the absolute value symbol is redundant. It doesn't need to be there. Think about plugging in 0. You get the absolute value of 0 plus 1, that's just 1. But if x is less than -1, think about -2. When I plug in -2, you don't have to write this down, but absolute value of -2 plus 1 is the absolute value of -1. So what I like, so the inside is going to be -1. To make it positive, I'll just double negate it. I'll add on an extra negative to make it positive. So let's see that in action, and then we'll ask some questions, though I can hold off for questions right now. Yes. What happens when it's 0? Then it goes into, then it's the absolute value of 0, which is 0. It doesn't really like, so this is an interesting argument that comes up. Does it need to be greater than or equal to and then less than, or is it greater than and then less than or equal to? That's up to interpretation. Some people will say that it should be on the right-hand side. Some people will say that it has to be on the left. Unless you are defining it yourself. If you are defining it, then you can kind of choose whatever you want. But let's see it here. So, if x is approaching 5 from the left, we're approaching 5 with numbers like 4.9 and 4.999. So x minus 5 would be positive or negative? It'd be negative. Because it's going to be 4.9 minus 5. That'll give me a negative number. So x minus 5 would be negative. So the absolute value needs to take account for that, and so it adds on an extra minus sign to take care of it. Thus, if x approaches 5 from the left, absolute value of x minus 5 is equal to negative the quantity x minus 5. This is like, by the way, if this is feeling a little bit weird, understandable. This is always the section that I get a lot of questions on. I've taught calculus for 7 years here, and every single time we talk about this, it's a little bit strange. But the more you practice it, the better you get at it. And we'll do it extra more. We'll do more. So this becomes, with that information from red, this becomes the limit as x approaches 5 from the left of negative x minus 5 over 2 times x minus 5. And now I can cancel them. Now that I have quote unquote evaluated, I haven't really evaluated, but I have taken into consideration the information given that x is approaching 5 from the left, which means that the inside of the absolute value would be negative. So as such, I tack on an extra negative to account for that, and I've dropped the absolute value symbols. That's me taking or evaluating the absolute value. And now that it's a factor and not an absolute value, it can cancel with the denominator, resulting in the limit as x approaches 5 from the left of negative 1/2, which is negative 1/2. Let's do the other side, and then we'll do another example. Right, do I have another one of those ones? Let me look at where we are in the notes to see what we got. One more page. Okay, so we're really good. We're good on time. We will. Oh yes, JT.
So it's only if it's like x or absolute value x minus a number.
In this case, yes. So here's the trick. I'll write it on, like, we're gonna add in a supplemental page or something in just a moment. But bonus, make it sound fun. The limit as x approaches 5 from the right of the absolute value of x minus 5 over 2x minus 10. So don't write anything down and just listen after you finish writing this, before we actually start doing things. We're approaching 5 from the right. So we're thinking about numbers like 5.1, 5.01. And therefore, will the inside be positive or negative? Positive. Therefore, the absolute value symbol is unnecessary. If we're approaching 5 from the right, all of our numbers are going to be positive anyways. So the absolute value symbol does not need to be there. So this is equal to the limit as x approaches 5 from the right of x minus 5 over 2 times x minus 5. The x minus 5's cancel. We get positive 1/2. Here is the trick in practice. In practice, plug in test value. If negative, drop ABS value and tack on negative. If positive, drop absolute value, and that's it. If when you plug in a test value, you get a negative number, that means that where you're approaching from, you get negative numbers, and therefore the absolute value symbol needs to take effect and needs to counterbalance the fact that the inside's negative by adding on a negative, an additional negative. If the inside's positive, then the absolute value symbol does not need to be there. So you can just drop it and move on. Case in point is this example right down here, which I'd like to leave for practice. Plugging in 1 from the left. So let's use our calculator to do a test value, like 0.9, right? 1 from the left, do 0.9. So 2 times 0.9 squared plus 5 times 0.9 minus 7. That's negative 0.88. So we would, so for this one, when you're doing this, you'll drop the absolute value symbol and write it as negative 2x squared plus 5x minus 7. Because you got a negative number. When you plugged in the test value, you got a negative number. That means that when you're approaching it, it'll be negative.
Say it again.
Sorry, 1 second. I'm just not fine. No, okay, it's fine. Yeah, it's a 0.99. It'll go closer, and then 0.999. Okay, yeah, cool. So to Eli, thank you for asking. So if you plug in something like negative 0.9, because you're approaching 1 from the left, I know it's hard to see. Let's zoom in. You're approaching 1 from the left. If you plug in 0.9 into this absolute value, like the function on the inside of the absolute value, you'll get negative 0.88. So the inside is negative when you approach from the left. So we tack on an extra negative sign to counterbalance the absolute value. Yes.
So approach right, then the negative symbol either.
Yes. So let's try that. Let's check that out. 2 times 1.01 squared plus 5 times 1.01 minus 7. We get positive 0.092. So when you go for numbers larger than 1, the inside is positive, making the absolute value symbol redundant. So we're out of time, but when we come back, we will do another example of this. So don't fret too much on this. We'll talk about it again. We'll do an extra example when we get back, okay? Once again, because of the injury my son had, I won't have office hours today. Sorry about that. But I will be back hypothetically on Tuesday for office hours. If you have any questions, email me. Otherwise, you guys have a great rest of your day. And I'll see you guys on Thursday for another brand new exciting lecture.